ambiguity in creative practices. Good to see old faces. Well, I should say old friends? Maybe not. Language is ambiguous. Through radically different expressions, one can convey the same idea. Think about how would you label the image on the screen. Would it be organic? Perhaps artificial? Psychological? As one can imagine, this task is open to each individual's view, informed by context and culture, and doesn't have an objective description nor a clear meaning. This problem differs from image captioning in a very fundamental paradigm. Creative practices, when working digitally, have adapted to encode the inherent vague and ambiguous natural communication into imperative commands in order to be produced by a computer. However, conversations and descriptions about art, design, or architecture are yet full of vague and ambiguous terms. As of the day of writing, it is impossible to design through natural language. Hypothesis. The use of data-driven framework through deep learning and natural language processing algorithms will provide the necessary state-of-the-art components that will democratize digital creativity, art, and design. Software skills for creative fields won't be as necessary as today. The Atari dataset is a collection of articles on creative fields such as art or design. The nature of the data is a vast variety of images and vague descriptions from the authors. In total, we have more than 200,000 images and text descriptions from different sections. The article you see on the screen is processed so that we only collect information relevant to each article. We only take the text between quotes and store the images. To manually curate the data, we built a GUI and tagged over 2,000 samples. We marked as valid those texts and images that were related in each sample.
Now we will discuss the binary classifier. Given how noisy the Atari dataset was, there existed a need to classify sentences and images as relevant or irrelevant. For example, the sentence "we wanted to display the anger of humanity" in the piece is relevant because it gives us more information about the images, whereas the sentence "I grew up on a farm" is irrelevant with respect to the images. We fine-tuned the 12-layer BERT model with uncased vocabulary and 2 labels for binary classification. The point of using this model is to remove irrelevant data from the dataset to result in better performing models down the line. Here are the loss and accuracy plots for the fine-tuning of the BERT classifier. After labeling our data, we had a bias towards negative examples, so we needed to ensure the quality of our model by running tests with an equal number of valid and invalid sentences. We exhaustively searched through batch size and max sentence length to find the best performance and found that BERT with an equal distribution had the best test performance when sentence length was 64 and batch size was 8, giving us a test accuracy of 70%. Whereas the best performance for the full dataset with an unequal distribution was with a batch size of 32, max sentence length of 64, resulting in 72% testing accuracy.
To build an intuition on how well our dataset would perform on generative models, we ran a classification task. The labels of each image comes from a bag of words of adjectives extracted from the text descriptions that accompany the image. We test 2 models, a CNN MLP encoded decoder network that applies one label classification and a CNN RNN model to perform multi-label classification. Both models take a pre-trained ResNet CNN network to encode the input image to a 64-dimensional embedding. Within the MLP one-label classification, we ran 4 experiments, from a 6 layers baseline to a 10 layers reduced vocabulary network. The performance of these models is far from good due to the diversity of the data. Relaxing the accuracy to a top K window is a more informative process. The RNN shows the best performance out of all the models. Here there are some label predictions shown from both architectures.
To create a baseline for modeling our image distribution, we built a small VAE CNN. We transformed all of the images into grayscale and reshaped them to be 64 by 64. We restructured our dataset such that the adjectives and images are paired in the following way, where one adjective can be paired with multiple images. We verified our model was sufficient by reconstructing test images, though given our model is still rather small, the images are still blurry. Now we wanted to gauge the quality of latent space image interpolation between images drawn from 2 different adjectives. We wanted the interpolated outputs to have captured some amount of adjective data such that the transition could reveal something about the adjective itself. Here are the examples. On the left, the true images were passed into the encoder, whereas on the right, sparse edge detection was used on the images before they were passed into the encoder. The interpolations from sparse edge detections are more fluid than those on the left. In future work, we are imagining that we need to develop some kind of algorithm or model to match images of different adjectives before they can be interpolated between. In this project, we introduced the first version of the Atari dataset for combining ambiguous text with artistic images. We calculated baseline statistics for the quality of the dataset with binary and multi-label classifiers and gave initial results for generative modeling with the Atari dataset. We also questioned the future role of artists, designers, and architects, and the extent that they might shift to a curatorial role rather than their current developmental role in artistic practices.